Hi guys, thanks for tuning in to another episode of Nuggets News. Today we've got some very special guests on, and that's AJ, the CEO of Qubit Protocol, and Gavin, the CCO, who's also professor at Macquarie University. So welcome guys.
Hi.
Thanks for having us.
And we're going to talk all about quantum computing, how it affects Bitcoin and cryptocurrencies, the applications of it. And I'm really looking forward to this because it's certainly a topic that I've found very interesting researching over the years. So how did you guys just quickly get into all this, and how did you apply it to cryptocurrency?
I'll let you go, AJ.
Yeah, so I studied physics in university, and then I basically got into cryptocurrency space through Republic Protocol, which is the last project that I did.
Yes.
So dark pool exchanges, while interesting, isn't really what gets me up in the morning. It's more about quantum tech.
Yeah.
So I reached out to some of the people in quantum tech that I knew, so Gavin, Marco, Troy, etc., and we just sort of came up with the idea because Gavin can talk a little bit about it, but he concurrently launched a paper in blockchain and quantum space. So from the entrepreneurship side, I sort of reached out and said, what can we do in this space?
Yeah.
And I got started into crypto last year when myself and some other quantum scientists decided to look at this question that was getting all kinds of hype in the press about the threats of quantum computers to Bitcoin. So there were all kinds of apocalyptic headlines about this is the end of cryptocurrency, and the Chinese are going to get some big machine. It's going to be a black swan that's going to fly in and destroy everyone's assets.
Yeah.
And so we actually did a careful analysis of the problem and looked at the actual threats, and then showed that on a realistic timeline, real threats to the security of the system is probably not going to happen for 10 years or more.
Fantastic, and we'll dive into all that today. So just to begin with, a basic overview of quantum computers versus normal computers. And one thing I think a common misconception is that quantum computers are very good at doing specific tasks and large number calculations. And a little bit like people might be familiar with, a CPU versus a GPU for doing graphics, and now we have ASIC chips that are made just to mine the Bitcoin algorithm. So do you want to give a brief overview of what they're good at and how they differ from traditional computers?
Yeah, so quantum computers, they're machines, but they're using the laws of quantum physics instead of the laws of classical physics that appear in our everyday life. And everything that's now in existence for computing is essentially, even when you get very down small into the level of transistors, is mostly using the laws of classical physics, where a particle is either in one spot or another spot.
Yes.
The current goes one way or another. That defines a bit. All your gates work off that principle. And what we realized, over the past 25 years of research in this area of quantum information, is that really you should take quantum physics seriously. And if you get small enough, you have to accept that things are going to behave like quantum mechanics behaves. And so now we have some prototype devices. Currently there's a 49 qubit device. Actually, IBM has a 52 qubit device.
Yeah.
Google has a 72 qubit device. It's not completely all wired up right now, but it's in existence. And we found that there are certain algorithms that quantum computers really speed up. And we probably will be more special purpose devices for these kinds of things.
Fantastic. So there's probably a few things I'll touch on just for the beginners in the audience to these concepts. So a few things you touched on there was Moore's law. A lot of people are familiar with that concept that, tech doubles in power every couple of years, but we're sort of reaching those limits in physics, aren't we? That the chips can't actually get any smaller. We're getting down to, talking in terms of actual atoms. So that is no longer going to continue in terms of progress. And the other thing you mentioned was qubits. So rather than computers having their bits, qubits and how that works and those numbers you mentioned, a 2-qubit computer isn't twice as strong from my understanding. It's an order of magnitude every qubit you add to the computational power. Is that right as well?
Yeah, so the memory doubles every time you add a qubit.
Yeah.
So things get exponentially large.
And some of those calculations that they're good at large numbers, so calculating collisions of lots of atoms or stars in universes and galaxies. Is that the sort of thing we're starting to see them being used for?
Yeah, although right now, some of the biggest applications are certainly cracking codes. So that's what really drove the field, was when Peter Shor in 1994 showed you could crack the RSA encryption and also elliptic curve discrete log encryption using a quantum computer. And this was a spectacular, this came out of nowhere. People were really surprised. Security agencies around the world were upset. And suddenly funding came into the field. Yeah.
So for maybe a brief understanding for people of how Bitcoin encryption works, public and private key cryptography, and how you can reverse engineer that once you have powerful enough computers, and that's kind of where this theoretical threat lies.
Yeah, so these things work on the idea of having one-way functions. So things that are fairly easy to compute one way and then hard to invert. And this is what allows you to do things like, send your credit card information over the internet. So you have, some initial random key, or, whatever it is, your dead cat's name, as a thing that will set up a private key, and you hope that no one knows that. And then this will then allow you to produce a public key. And then you go through some mathematical manipulations, like elliptic key cryptography, where you're just looking at how the point on a curve jumps around as you apply it many times. And doing that step is easy, but then inverting it from the receiver's end and everyone who can see your transaction, it's very hard for them to figure out what your private key is from the output of that.
Yeah. Did you talk about maybe how this works in terms of traditional Bitcoin mining and cryptocurrency mining that have proof of work algorithms compared to how it might work with quantum mining?
Yeah, so with the proof of work mining, the idea is that you've got these blocks that are on the blockchain, and you have a bunch of candidate transactions, and you want to have someone verify those transactions. And so there's a header on this block which contains timestamp information and also a hash of the previous block, and something called the nonce, which is a string of bits which can be adjusted and changed. And what you want is someone out there, a miner, to solve this problem where if you apply a double hash to information on the header of that block, then there should be an output which has some number of zeros on it.
Yeah.
And then, so basically the classical computers just have to try hash after hash after hash. And eventually they'll get lucky. Hash is thought to have no structure, so there's no fancy kind of manipulation you could use to speed that up.
Yeah.
Quantum computers do all this at once. So rather than trying hash by hash, they try all the hashes at the same time using Grover's algorithm, where you put the computer into a superposition of all possible listings of the header and nonces, and then in a square root of the number of hashes, it will spit out the number. So that's the idea.
Fantastic. Do you want to talk about the other findings of that paper you did in terms of what you think the threats to Bitcoin and other similar algorithms are, and how far away that is?
Yeah, so what we found with the mining is that you really have to be careful when you would analyze these things, because quantum computers have errors just like classical computers, just like your cell phone is doing error correction all the time. And to cover up for errors, because there's more types of errors quantum computers can get versus classical, you have to add in a lot of extra qubits, a lot of extra processing. There's these things called fault-tolerant quantum computing protocols, and that pushes up the resources you need into the millions of qubits and tens of millions of gates. And if you do an actual faithful analysis where you include the fact that there's a quantum Moore's law, with the doubling of qubit numbers and quality and speed, then actually we're a very long way away from even getting quantum computers close to something like the Antminer ASIC device of today.
Yeah.
So yeah,
people shouldn't be expecting, quantum computers in their phones or home computers or mining cryptocurrencies anytime soon. In about the next 10 years at least, you're sort of saying.
yeah, and I mean, what's going to happen most likely is it'll be a kind of cloud computing.
Yeah.
So you'll send, and what's cool actually with quantum, you can send not only the input to a distant quantum computer, say you send something off to Google, but you can also hide the algorithm you're doing. And that's actually different from what can be done with classical computers securely. Awesome. So yeah, you can fake that you're trying to crack a code and do it on the cloud.
Absolutely. And I don't want to jump around too much, but why this is so interesting and a few of the concepts for people that don't know, in the world of physics, the very large objects have different laws to very tiny objects. And some of the most interesting things to me when I was learning about this and watching documentaries are wave particle duality. So the fact that something can be, a wave and a particle at once. It can be in those superpositions, as you say, so two states at once. And when we have that, we can have quantum entanglement. So two atoms can be very far away in the universe, but actually relate and affect each other. And the same as when we observe those atoms that might be in different states. Once we observe them, they can only take on one state. So the fact that observing something in the universe can change reality is just, you can go down the rabbit hole forever once you start talking about these things. It's just so fascinating. I love it.
Yeah, that's why I do it for a living. I love it.
So what's the Qubit protocol's aim? I know you guys are starting a DAO, and our audience is pretty familiar with DAOs, and you guys want to fund the best projects because you believe, I guess, you're as intimately familiar with this industry as anyone.
So I think the biggest goal for us is that, as Gavin mentioned, there was a lot of media around how quantum computing is going to disrupt Bitcoin and how the physicists are going to steal all your Bitcoin and Ethereum, and everyone's at risk. And then Gavin's team, and when we did the paper, we disproved a lot of that and said it's actually going to take 10 to 15 years before this becomes an issue to mining. So it's really just the misconceptions around quantum computing, around quantum tech, and allowing us to fund the projects that should be funded and actually have technical merit, as opposed to the projects that might be misguided or a misconception and to what they're actually doing, right?
Yeah.
So, for example, everyone's focusing on quantum computing now, but that's probably one of the far off technologies. I think what people should be focusing on is quantum sensors and quantum secure communication.
Yeah.
Or even looking at ways and how quantum key distribution could be used for the blockchain, for example. So there's a lot of cool applications that I think people just sort of miss, and that's the goal for our protocol.
So as we said, those everyday applications might be years away. So do you want to touch on some of those things, or why would someone get involved with this project if some of those things are so far away? What are the good applications that, and as you said, these computers are already working. This isn't theoretical. So what's a bit closer to reality?
So as Gavin mentioned, we're about 72 qubits. It's not wired up, but that's sort of what we have at the moment. And the thing is, quantum algorithms, so quantum computers are really good at certain algorithms. So there's probably around 100 and 150 algorithms that work right now that we've discovered. But the issue is it doesn't actually work for things like your mobile phone or, graphics, rendering graphics, etc. So there's a lot of algorithms that we can't solve.
Yeah.
And because of that, tomorrow someone could come up with a universal Turing machine for quantum computers, which means that we can put a quantum processor in a laptop, which would be awesome. But for now, I think quantum computing is 10 to 15 years off, but I think the near-term applications are going to be stuff like nano MRI, using quantum computing for MRI imaging to make it more efficient. Quantum secure communication. There's a company doing a satellite QKD, quantum key distribution, which Telstra and BT Group are behind. So I think the near-term stuff is going to be around telecommunications and sensors as opposed to actual computing.
That's awesome. And what are some of those issues that quantum computers are facing? They have to be kept near zero. Is that why they're sort of these big machines at the moment that aren't going to be in your phone anytime soon? They get very hot. What are the other sort of headwinds for this space?
Yeah, so you have to keep quantum computers really isolated and really cold, generally. I mean, the leading candidates right now are using superconducting qubits, and superconductors, these things are cold. They're, below 4 Kelvin.
Yeah.
They're the, big, isolated machines that are, in manufacturing, you have to use clean rooms, just like you do with classical chips.
Yeah.
So yeah, they're big things and cold.
In terms of current cryptocurrencies, we've covered Nexus on the channel. I'm not sure if you guys are familiar with that, but that has a quantum resistant algorithm. If this all comes along maybe quicker than we think, and let's say it's here in 5 years' time, Bitcoin can hard fork to a quantum proof algorithm as well. I think there's a lot of people that think, this is all over, but there's very much ways for cryptocurrencies to just implement quantum proof consensus algorithms.
Yeah, actually, with Bitcoin, it's possible to do a soft fork, actually. But I mean, it is an issue that, there are a lot of addresses there. There was a recent analysis done that showed that up to a third of Bitcoin out there would be vulnerable if there were, say, a quantum computer, tomorrow that could work out their private keys. But the general advice is always true: don't reuse addresses, and Bitcoin could accommodate this with a soft fork.
Yeah. And just quickly, for why we recommend using new addresses each time is because of that reverse engineering we're talking about. So if someone knows your public key, they can theoretically calculate your private key, guys. But if you're always using a new address, it's less likely that people know your public key.
Right.
Cool. Well, any final messages, guys? It's been a fascinating chat. I'm sure we'll get follow-up questions and probably have you back on the channel because this is a deep topic.
No, I think the main thing is that, quantum computers, the biggest threat is going to be on digital signature encryption, as we talked about. I think mining is probably far off, but when you're talking about digital signature, we can probably crack that in 10 minutes within the next 10 to 15 years, optimistically. And I think it's more about how long it takes for us to hack it as opposed to whether we can hack it at all. So the biggest defense is, not reusing addresses and making sure that, as a community, we look into stuff like post-quantum cryptography and other solutions that we can use. But I think for the meantime, we're all safe. Yeah.
Cool. Any final thoughts there, Gavin?
I just want to add, there's a question I get most asked about Bitcoin is power usage. People hear it's 95% of the power consumption of the country of the Czech Republic. And that's really depressing. You start to wonder, is being in crypto a good thing for the world?
Yeah.
And, ultimately, when we talk about better computers like quantum computers, these things can work reversibly. The power consumption can be a lot less. And there's even some new future